right. Here we go. All right, so on your sheet that you just got, this one right here, it's got a periodic table on it, and it's got history, facts, trends, and patterns. We're going to start at the top and work our way down. Now, as we go here today, you don't have to write every single thing down. I'm going to kind of condense it down so that we can hopefully rip through this. So here we go. But we're going to start with the history of the periodic table. You don't have to write this down, but it's just good information. By 1860, there were over 60 elements that have been discovered, which got scientists wondering, how do we organize them, and is there a relationship? Okay, they had been working on lots of different things since like the 1700s. They started doing quantitative experiments, all right? Up until like the 1700s, the only science really that had been done when people would philosophize, is that a word? Anyways, they would think about stuff. But nobody really did science experiments until around the 1700s. And then they started recording data and collecting information. And by the 1860s, you had this whole big mess of data that was not organized in any fashion. So you had several people start to try to get it together. They started trying to organize stuff. So you have this guy, Dmitry Mendeleev. He is the original creator. So right there on your paper, where it says original creator, somewhere under there, you're going to put Dmitry Mendeleev. That's the name you want to write right there, Dmitry Mendeleev. He organized the elements based on their atomic masses. All right. So if you know that Mendeleev organized it by mass, Mendeleev organized by mass. That's the main point that you need to write down. Mendeleev organized by mass, based on their atomic masses. Okay, when he did this, he saw that many of the elements had properties that appeared at regular intervals. And he said, and he noticed that a repeating pattern is known as being periodic. If you say that there are patterns of behavior, for instance, like you could say that the cafeteria serves Crispitos periodically, right? Because we know that they will serve them on occasion. It's the best day of the year, right? Crispito Day, all right? But it's served periodically. There's a pattern to that behavior, all right? Mendeleev created a table of elements based on their characteristics and their atomic masses. He also suggested the periodic law, which says that physical and chemical properties are periodic functions of their atomic numbers, which is just their proton number. In other words, they're going to act according to how many protons they have. Their properties are based on protons. All right. So then you have this guy, Moseley and the periodic law. Okay. Moseley is the creator of the modern periodic table. So on your paper, where it says modern periodic table creator, you're going to write Moseley. Moseley. I know. It would have been easier if like Mendeleev would have been mass and Moseley could have been like an N, like Nosley, number, a bit easier. C'est la vie. Okay. Moseley arranged the periodic table by number. Henry Moseley. And this, by the way, is the early 1900s. This occurred maybe like 1912-ish, early 1900s. Henry Moseley, though, took the pattern that was arranged by Mendeleev in the late 1800s, and he started evaluating it. The problem with arranging it by atomic mass is there were some glitches, okay? So let me show you. If you're looking at the periodic table, and you can flip your paper over if you wanted to, or if you just want to look over here at Ashton. And if you're looking across the chart, yeah, there you go. If you look across the chart, occasionally you can find little places in the chart that normally the patterns will increase as you go across the periodic table. The atomic masses increase. But occasionally you'll find some spots where it dips back down and then it goes back up. So let's see if we can spot one of them. 52, is it 52? Or T. Oh, yeah. Okay, yeah, so 121, 127, 126. All right, and there are 2 or 3 different spots on the periodic table where you have this. It doesn't fit the pattern. So there were a few small glitches with Mendeleev's table, but hey, and we can't give Mendeleev, Dmitry Mendeleev, you can't give that guy too hard of a time because he did something very substantial. He was able to take all of those elements that they knew of at the time and come up with a pretty good pattern. He organized them to where you were able to predict other elements that had not been discovered. Mendeleev, the guy that we just talked about, he, as a matter of fact, predicted that there were like 3 undiscovered elements that would be discovered, and he even picked out which family or group that they would go in based on their properties because his table was so good. So even though he arranged his table by mass and there were a few glitches, for the most part, it was a pretty good way of organizing it. Henry Moseley came along about 20 years later and said, you know, I think what would fix this is if we arranged it by proton number, by atomic number. So that's what they did. Okay. Another interesting thing about Moseley, you can see in this picture, he looks pretty young, right? Moseley, what we'll find in science this year is that a lot of these guys got caught up in political, there were political things going on at the time. The guy Lavoisier, Antoine Lavoisier, who came up with the law of conservation of mass, he did a lot of his work in the 1700s during the French Revolution. He got his head chopped off with a guillotine during that time. Henry Moseley was a great scientist for Great Britain, but he wanted to fight in the war for England. And so during World War I, he actually got shot and killed by a sniper. And so the British Parliament put a law into play, though, that said, we'll never do that again. If we've got a scientist that's wanting to go to war, they can go fight for their country, but they're going to have like a desk job. They can't go out in the field. So, but that was Henry Moseley. He died like when he was in his 20s, I think. All right. So that's crazy, though. Like he made such a substantial like contribution to science, like before the age of 30. That's impressive. Okay, so let's talk about the periodic table of the elements. Okay, we know this table. We looked at it for years, right? We've probably seen this at least the last couple of years. Okay, so let's talk about famous families. Oh, sorry, let's go back. We missed one. Vertical. The vertical columns in the chart, so the ones that go up and down, the vertical columns in the chart, those are called groups or families. Groups or families. The vertical columns are called groups or families. Okay. And those groups or families, just like a real family, have characteristics in common. They behave in a certain way. They're all alike. Or they'll look a certain way. Okay, they'll have a certain texture. All right. The rows, the horizontal rows in the chart. So right there, the horizontal rows in the chart. Those are called periods. Periods or energy levels. So the horizontal rows, so that's what you're going to write right there, horizontal rows. Those are called periods or energy levels. So if you're looking at the periodic table, how many rows or energy levels do you see? 7. There are 7. There are 7 rows or energy levels. And each one of those energy levels can hold a certain amount of electrons for an atom. Okay, and there's a little formula that you could do to figure this out. And we'll talk more about that formula next week. But I know that a lot of you last week kept talking about, well, the rings around the atom, can't they hold like 2 electrons? And then the next one can hold 8, and the next one can hold 18. And the answer is yes. There's a certain amount of electrons that each energy level can hold, and there's a formula that goes with it. It's called 2n squared, 2 times n squared, where the n is just the energy level. You pop in like level 3, and you do 2n squared. So 3 squared 9 times 2 is 18. So the third level could hold 18 electrons. But we'll come back to that next week when we start talking about bonding a little bit. Okay, so now let's go to famous families. Here we go. There's going to be, I think, 1, 2, 3, 4, 5 of these. So there's 5 of these famous families that we're going to talk about. And remember, families are columns. They're the vertical columns. Group 1, those are the alkali metals. Group 1, those are the alkali metals. They're very reactive metals. Okay. Group 2, that's the alkaline earth metals. Group 2, those are the alkaline earth metals. Groups 3 through 12, those are going to be your transition metals. Okay, so let's take a look here. So group 1, way over here to the left of the periodic table. And if you want to look at the periodic table on the back of your sheet, you could. Group 1, these are your alkali metals. These are alkaline earth metals. These are extremely reactive. If you put these in water or you just leave them open to air, they explode. They're very, very reactive. These things right here will hardly ever exist on their own alone in nature. They can't. They'll exist in compounds with a lot of stuff, like Na. Where have you heard of Na before? What's it usually hooked to? Yeah, salt, NaCl, right? All of these will tend to be hooked to other things just because they're not stable enough to be on their own. This one right here, group 2, these are your alkaline earth metals. Still very reactive, but they can sit in there on my cabinet and be okay. You know, you could have magnesium metal set out and it would be okay. Over here, groups 3 through 12, so the middle step right there, those are your transition elements. Okay. The transition elements, those are the ones that we notice, like that we've heard of usually, like iron, copper, gold, silver. Those are the elements that we know about, right? That we're pretty familiar with. But there's other ones in there that we use, but maybe we don't know that they're there. Tungsten, for instance. You see where W is, number 74? Tungsten. Number 74, that's called tungsten. Tungsten used to be used to make filament for old light bulbs. You know, we have the fancy LED light bulbs now, but the old light bulbs had this little tiny piece of wire that was all coiled up, and that was tungsten wire. The reason why they would use tungsten is it can handle a lot of heat. It can get really, really hot without breaking. Now, eventually, would it break? Yeah. And you could take an old light bulb, and you know when it went out because you could shake it, and you would hear something rattling around in there, and that was the tungsten that had broken. But silver, gold, platinum is over there, number 78. Platinum is a very nice, expensive metal. Zirconium, ZR, boys, if you go buy your girlfriend a diamond engagement ring and it's cubic zirconium, they have ripped you off. Zirconium looks just like diamond, but it's way cheaper. If your girlfriend finds out, well, that's over. Okay. All right. But those are some metals that are in that group that you may or may not know about. So far, what would you say the bulk of the periodic table is made up of? Yeah, and just metals, right? Just metals in general. Most of the elements that we know about are metals. Okay. And then we get over here to the right side of the chart. As you move across the chart from left to right, they get less and less metallic. And finally, you get over to the right side of the chart. Group 17, those are called the halogens. Group 17, those are called the halogens. And these are your very reactive nonmetals. These are your very reactive nonmetals. These are the ones that cannot exist on their own. You won't find fluorine atoms, just single fluorine atoms floating around out in space. They will always be hooked to something else, either another fluorine, so you'll have a fluorine molecule, or you'll have fluorine hooked up to Li, lithium fluoride. You'll have one of the superactive metals hooked up with a superactive nonmetal, and they make something called salt. In science, when we talk about salt in science, you're not just talking about sodium chloride, you're talking about any active metal that's hooked to an active nonmetal. So lithium fluoride could be salt. Sodium chloride could be salt. Potassium bromide, that's salt. Any active metal hooked to an active nonmetal, that's considered salt. All right, so those are the halogens, group 17. Those are the very reactive nonmetals. Most of those are gas at room temperature. Oh, by the way, so if you're looking at this periodic table over here, you'll notice that there's stuff in the black letters, blue letters, and red letters, right? Like they're color coded. What do you think that tells us? You have any idea? Black letters, red letters, blue letters. Yeah, solid, liquid, gas, states of matter. So the black letters are solids at room temperature. The blue letters means it's liquid at room temperature. And then the red letters means that those are gases at room temperature. Those are the nonmetals, right? So what's your only metal that's a liquid at room temperature? See it? Hg, mercury, right? Find it in a thermometer. How about your only liquid nonmetal? Br, bromine. Yeah, bromine will exist as a liquid at room temperature. And then the rest of those guys are gases. How about the white, the clear letters? What do you think that is?
Plasma.
No, but that's a good guess. Not a bad guess. That actually just indicates those are synthetic. What does synthetic mean? Man-made. They're man-made. They're made in a laboratory. So all the ones at the bottom, those have been made in a science lab somewhere. They don't know that much about them because they usually don't last very long. They create them and then they disintegrate. So, all right. Group 18. Here's another famous family. These are your noble gases. So your unreactive nonmetals. Your unreactive nonmetals. Your noble gases, unreactive nonmetals. Okay, and these are the ones that you hear about, like helium. You know, you can fill up balloons with helium. You can do all kinds of cool stuff with your voice if you suck down a bunch of helium, right? Don't do that all the time. You know, killing brain cells. So, do what?
I won't do it again. It scared me.
Oh, I loved it. I sound super cool when I suck down helium. But, you know, and like, I think, have we talked about that in here? It's either like krypton or xenon that will make you sound like Satan if you suck that one down, right? Yeah, so look it up. It's really cool. But that's another one. It's just because of the density of the gas. Okay, helium is extremely light. So when you suck down helium, it kind of takes the pressure off of your vocal cords. So it makes them go really high. And if you suck down like xenon or krypton, whichever one that is, it's so dense. That gas is so dense and heavy, it squishes your vocal cords and makes them sound really cool. Okay, so don't try that at home, but you should totally look it up. All right. Now, before we move on, though, oh, I forgot. We need to look at some color coding. So I'm going to see if I can switch over to the ladybug here. We're going to color code this a little bit. Bloop. Maybe if I can get it to work. Oh, yeah, I don't think my ladybug's going to work on this. Shucks. Anyways, so if you are watching this at home, you're just going to have to take my word for it. maybe, let's see if I can do this. I'm going to go back to this. I'm going to stop presenting. And I'm going to do this. Stop sharing, maybe. We'll try that. Okay, well, maybe not. I was going to try to show the what we're doing on the periodic table, but hopefully you can just look it up at home if you can't figure it out. Let's see. Okay, so let's go back to this. Who's that now? Share screen. Nope. Share. Wait, that's not working. Oh, well. On your periodic table, what you're going to be doing is we're going to color code it. I can't figure out how to get that to work. So we may stop that for just a second, stop recording and see if we can do that.